everyone, let us continue with the 4.3 force on a moving charged particle in a uniform magnetic field. So this is a charge moving in a uniform magnetic field. This is the north, this south pole. Okay, so you can see the direction of the particle. Okay, right. A charge move with a velocity v in a magnetic field B will experience a magnetic force using the formula F equals to QV cross B. The magnitude of the magnetic force can be calculated using the formula FB equals to QVB sine theta, where FB equals to magnetic force, Q is the magnitude of the charge, V is the velocity of the charge, B is magnetic field strength, and theta is angle between V and B. The direction of F can be determined using the right hand palm rule. Your thumb will represent the velocity of the particle. Fingers will represent the magnetic field B, and perpendicular to your palm is the direction of the force. Okay, this is true for positively charged particle only. If the moving charge is negative, the direction of the force is opposite to that indicated by the right hand palm rule. What that means is the direction of the force will be at the back of the palm. Okay, so this is for the negatively charged particle. Okay, so you have to make sure you understand that concept. Okay, right. Let's try your understanding using these four cases. Okay, so we have to determine which is the direction. What is the direction of the magnetic force on a charge that moves as shown in each of the four cases shown in figure below. Okay, let's take a look at case A. What happened here? So you got the dot, dot, dot. What the meaning of the dot here? The dot means that the magnetic field is out of the page perpendicularly. Okay, so what type of particle is this? So this is the positively charged particle. And where is the direction? Okay, the direction is downward. So this is the direction of your thumb. Okay, you have to direct it, and you have to use your finger into the out of the page, and so the force would be okay. So using this is your thumb downwards. Okay, so your finger will be out, so your force would be to the left. Okay, right. Okay, for the next case, what we have here, you are given the B to the right, so your finger should be to the right. The V is upward, so your thumb would be upward. This is the positively charged, so where should be the force? Okay, so the force should be into the page. Okay, so you have to do on your own, using your right hand. Okay, the third case here, the magnetic field. Okay, you see here, this is a cross, cross, cross. What does it mean? It means that the magnetic field is into the page. Okay, so this is the negatively charged particle, and the direction is to the right. So your thumb would be to the right. Your finger should be into the page. So this is negatively charged. So where should be the force? Okay, if you put your palm here, you will get this, right? So the V to the right, okay, using your thumb here, your finger into the page, and you should get force upward. This is true if the charge is positive. But then this is a negatively charged particle, so the direction should be downward. Okay, you must remember this. Right, and let's go to the last case here. We also have negatively charged particle, but it's moving to the left, and magnetic field is to the right. So what happened here? It is a parallel cases. That means V and V is parallel. Using the formula FV equals to QVB sine 180 degree. Sine 180 degree means we got 0 here. So the magnetic force will be 0. Okay. Okay, let's take a look how the motion of a charge in a uniform magnetic field. Okay, so this is for the positively charged case. Okay, a magnetic force will exert on a charged particle. So, for example, this is the positive charge. Okay, right. F of B is acting on the charged particle is always perpendicular to V. Okay, let's take a look here. Yeah, so V at point 1 here, V is to the right. Okay, so F should be using your right palm here. So V to the right, your force should be perpendicular to your palm because the B is into the page. Yeah, so direction your finger should be into the page. So the force should be upward. Okay, so because force is always perpendicular to V and directed to the center of the circle. Okay, under the action of such force, the charged particle move in a circular path. Okay, let's take a look at point 2 here. Yeah, when it reach here, the particle move and it reach at point 2. So V is upward. If V is upward, okay, so you take your thumb upward, your finger into the page, so the force on your palm should be to the left. Okay, then at point 3, the V is to the left. Okay, B is into the page, therefore the force should be downwards. Okay, and at point 4, V is downward, that is your thumb here. Your finger should be into the page and the force should be to the right. Okay, since it's moved in a circular path, we recall in our chapter 6 in semester 1, that is FB equals to FC. Okay, so we have known that FC equals to mv square over r. Is from uniform circular motion, yeah, chapter 4, topic 6, semester 1, SP015. Okay, right. So from this equation or relation, FB equals to FC, we know that F of B for charge is QVB sine theta. The theta should be 90 because it's always perpendicular. Therefore, it always be 90 degree. Cannot be more or less than that, right? And we use the Q because it regarding the charge, okay? Charge particle is equals to, this is for the centripetal force, okay? For the circular path, the mv square over r, okay? So from this equation, you rearrange, you can get the radius of the circular trajectory is equals to mv over qb. Okay, so from this equation, we know that r is directly proportional to v and r is inversely proportional to B, that is the magnetic field. Right, and from this relation, we also can get the period of revolution. Yeah? From period of revolution, we know that T equals to 2 pi R over V. Yeah? This is a general equation we have learned before. Okay, so we substitute the R with mv over qb, so we can get that T equals to 2 pi m over qb. Okay, right. Okay, let's take a look at the example. Okay, calculate the magnitude of the force on a proton traveling 5 times 10 power of 7 meter per second in a uniform magnetic field strength of 1.5 Weber per meter square. If the velocity of the proton is perpendicular to the magnetic field, and B, if the velocity of the proton makes an angle 50 degrees with the magnetic field. We are given the charge of the proton is positive 1.6 times 10 to the power of negative 19 coulomb. We are given V equals to 5 times 10 power of 7 meter per second, B equals to 1.5 Weber per meter squared, theta equals to 90 degrees. Therefore, using the formula QVV sine theta, okay, you just substitute the Q given is positive 1.6 times 10 power of negative 19. V is 5 times 10 power of 7. B is 1.5. And theta is 90 degree. Okay, so she should get 1.2 times 10 power of negative 11 Newton. Okay, and then for the next question, you are given theta equals to 50 degrees. So, just substitute the formula FQVB sine theta. Yes, Q is the same value. Yeah, V still 5 times 10 power of 7. Okay, B for magnetic field is 1.5. And angle would be here given theta equals to 50 degrees. So, just plug in their value in your calculator and you should get the answer. Okay, so you should get that 9.1925 times 10 to the power of negative 12 Newton. That's all for 4.3 regarding force on a moving charged particle in a uniform magnetic field. Okay, we will continue on subtopic 4.4. That's regarding force on a current carrying conductor in a uniform magnetic field. Thank you.